This is an introduction to chemistry. We will study the branches of chemistry, the scientific method, and experimental design in the next set of slides. The first thing we're going to talk about are the branches of chemistry, and you can see here the ones listed: organic chemistry, inorganic chemistry, analytical, physical, and biochemical. And organic chemistry is the one that's associated more with carbon compounds, and those are all associated with living and life. Inorganic is the thing that what we're going to be studying, and those are the non-carbon compounds and what we'll be studying. Analytical deals with more the math or the composition of the samples and what they're made of. Physical deals with the behavior of them and what energy they're able to tap from them. And then biochemical are the ones that are associated with what we understand as life. The next set of notes that we need to learn about is the scientific method. You should have learned this already and have probably been learning it since you were in a much younger grade. Basically, the scientific method is a way to solve a problem, and it's the scientific logical way. You probably have learned multiple different steps with this. Some places, or some people have as many as 8 to 10 steps and as few as 3 to 4. We're going to learn 4 basic steps in here to the scientific method. They can all be broader as you go through, but this is the 4 that we're going to use. And the first one, observations. When you're making observations, you need to think about what it is that you're using your senses to obtain. What are you seeing? And it's probably one of the areas that you can make the biggest amount of mistakes in chemistry is by not observing close enough. You want to hurry up and get something done, and that's when you miss something small like the gas bubbles or a small odor or even a temperature change because you just didn't check for those things. And so that's something that you really, really need to be careful about. And when we're dealing with chemicals and things, is that you slow down, take your time, and really look at the different things as you make the observations. Formulating a hypothesis. A hypothesis is just simply an explanation for the observation. Why did it happen? I like to use the if-then statement. If this happens, then this will be the consequence. And so that kind of helps us to look at those observations. So let's say we had a burning candle, and we might say, if the candle goes out, then it didn't have oxygen. Or if you blow on the candle, then it will go out. And so that's kind of what you're looking at as far as the hypothesis. And so you want to be able to do that for each of those different observations. The next step that we're going to go through is testing hypothesis through experimentation. And a lot of the time that we're going to be experimenting on things, that this step is already going to kind of be written out for us. But this is where you get the open-ended, being able to test different things and look at different things. And some of the things that I'm going to be asking of you is that when we're going through the experiments, that you kind of go above and beyond and you think, what would happen if we use this? And that's where you get those new hypotheses from is by questioning, if I changed this piece of this project or what experiment we're doing, then how would we be able to do that? The key with this is you have got to have a detailed set of procedures, very clear when you're going through this, because otherwise you may get a result and you may not be able to duplicate that test. Another reason you want a detailed set of procedures is because when you have finished a test and let's say something really cool happens, then you want to be able to duplicate that, because otherwise then doesn't do you much good if you're not able to duplicate it. And what you're looking for here is the reliability of your results, that over and over and over again they kind of withstand the test of time. And that's how we come up with new and different things in experiments, and how scientists in general come up with new and different things is over and over and over their test is. We should only have, when we're looking at experimental design, one manipulated variable and one dependent variable. A manipulated variable is also oftentimes called an independent variable, and I want you to think about that as what it is that the scientist is changing. And so in an experiment, if we're testing, for instance, let's just pick one. If we're testing whether or not grape jelly on a peanut butter and jelly sandwich is preferable to strawberry jelly, you can't change the style of peanut butter or the style or the kind of bread or any of that, because what you're looking at is whether or not it's the grape jelly that's preferred over the strawberry jelly. So everything else would have to be held in check. So that's what I'm talking about when I say you can only change one independent or manipulated variable, what it is as a scientist that you're manipulating. The dependent variable then is what we're looking for is when we change that independent variable, what we manipulate, when we change that, what happens to the dependent variable? And oftentimes the dependent variable is the test. What are we trying to measure? What is it that we're looking at? And what do we want to what values do we want for that? For example, on the examples there, the effective surface area on solubility. If we have a larger surface area, so our liquid is more spread out, is that going to make our liquid more soluble or less soluble? And then how much effect does temperature have on pressure? If you raise the temperature, does your pressure raise? Those are the kind of things we're looking at, and those are the kind of tests you really have to think about when you're doing your own testing, is are you manipulating more than one thing, and what things are going to change that. So you want to be careful with those. With that experimental design, we do need to remember that we often need to graph our results, and it's a lot easier. And if you're looking at a set of material, a set of data, that it's graphed and it's drawn out so that you're not digging through the material. The manipulated variable or the independent variable will always be on the x-axis. If you can remember the acronym dry mix, sometimes this helps a little bit in remembering that, and the y variable will always be on the y-axis, the dependent variable will be on the y-axis. So what we're looking for is that we remember that when we're doing our graphs. Also, with experimental design, our results can show either direct relationships, which, the direct relationship and the direct correlation there when that line is going straight up, and then it could also go down. Don't think that couldn't happen, but what they're looking for is it is a direct relationship. As this goes up, then the change, as the variable changes, then it goes continually up or continually down. When you have an indirect relationship, you could either have the bowed relationship you see there where it does not create a straight line, or you could also have where it's kind of scattered all over the place. And if it's scattered all over the place, your test is probably not a really good test for what you're running. So you want to be careful when you get a result. Another couple of things that we want to talk about again, we should still be careful to only change one variable. If you change more than one variable, your experiment is just not reliable, dependent, or anything else. So you really have to be careful with that. That could be the amount of water you're using or the amount of something that you're using. For example, you should also use the same equipment for each trial. So you want to be careful that you're not changing up graduated cylinders and you're not changing up beakers. The other thing that you need to remember when you're designing an experiment is that you conduct each trial under the same conditions so that stays consistent as well. You don't want to have, let's say you were doing an experiment outside and then one day it was really, really sunny and hot and the next day it was cool and cold. And so you want to make sure that you conduct it on the same experiments because that could throw off. The last couple of things that we want to talk about is you should always have a control. This is a trial in which the manipulated variable is not changed or used for comparison. And what they're talking about there is you keep one control group so that that is not what is being changed, and making sure that the manipulated variable is not changed in that group so that you're able to compare with the norm. You should also average the test results of many trials. 1 or 2 trials is not going to be enough to make a significant statement of your data and making sure that your results are accurate. You need to have it, probably at least 10. That's one problem we're going to have with a lot of our tests. We won't run that many trials just simply because it takes a lot of chemical to do that. And so the more trials you run, the better your reliability results would be. So if you were actually doing something new, you would need to run many, many, many trials to get that accurate. Results should be reproducible, by other scientists. And all that's saying is that if I gave your papers to another group, if we're writing up in an experiment, and if I was asking you to, for instance, make a peanut butter and jelly sandwich, you need to be able to write those so that I can give them to another group and that same group could produce those results. So you have to be very careful that you write those procedures exactly like they need to be. And that's also why we need to learn to follow procedures exactly as they're written. We should report all results, not just the expected ones. Just like in basketball, you can't take back the shots that don't go in, that hit the rim. Well, that's the same thing in a science experiment. There may not all be like you want them to be, and you can't just erase the ones you don't care for or don't like. So once we get to that point then, and these are some things that we definitely aren't going to be doing in here, but just so you know where you go next, then once you have these experiments and you found something new, then you develop a theory. And once a hypothesis meets the test of repeated experimentation over and over and over again, then it may become a theory. And a theory is a really, really long explanation of why something happens and pretty detailed explanation of that. Theories can be changed at some point because there may be something new come up that they didn't know at the time, and that changes it just a little bit. So theories are oftentimes changed. The last thing that will happen then is after it's a theory, or the other side of that, is a scientific law. And a scientific law is the mathematical statement of why something is happening or what has happened. Scientific law doesn't try to explain the relationship, it simply just describes it. This is what happens. That explanation requires a theory. The theory is the why, the scientific law is the what does. As we go through that, here's a little flow chart that may help you. We always take those observations. All science experiments begin with observations. Ours are going to begin a little bit more with me directing you to it, but there's a reason for that. And so you want to observe in nature and ask questions about things. Why is this happening? Why does this happen? And you want to do that. And that hypothesis then would be I think it happens because of this. And so you're giving a reason for why that observation may have happened. Then you do the experiment. And you notice that there's a circle there between the hypothesis and experiment, because sometimes it takes, once you do an experiment, you may take a turn and go, I don't think this looks right. And so you may then make a new hypothesis. And that circle sometimes is fairly extensive when you're circling around in there. Then eventually your hope is if you're a scientist that you are able to produce an experiment that then turns where you're able to get a theory from that. And you notice the theory and the experiments go over and over again, because once it's a theory, that doesn't mean you just stop testing it, because then other people are going to be testing it and trying to prove it wrong. That's part of science. And then underneath the experiments, we see scientific law there. Again, reminder that scientific law is the what happened and the data of that. So that's where we're looking at there.